Good afternoon, everyone, and welcome to this presentation. I'll be talking about picodroplets for cell line engineering, our novel automation approach and the benefits that it can bring. So let me tell you a little bit about sphere fluidics to start. So our mission is to help our customers find, analyze and isolate the most valuable cells easily and quickly. We're based in Cambridge over in the UK, and we've got over 300 customers today across the globe and growing rapidly. We've got a large product portfolio and a substantial IP portfolio, well over 150 patents now. I'm Richard Hammond. I'm the Chief Technical Officer at Sphere. I joined in late 2022, and I've spent most of my career working at the intersection of biology, hardware, software, and how you bring those technologies together to do really interesting things. So during this talk, I'll introduce you to our Picodroplet technology, why it's a key enabling technology for life sciences, and particularly how we're using the technology to resolve some well-known challenges in cell line engineering and development. Cell line development, it's a cornerstone of biologics development. That ability to produce a therapeutic structure to the right quality and cost is absolutely fundamental to success. But that process has some well-known challenges. Firstly, time. Developing a cell line is time consuming, it's labour intensive, many technical challenges you have to overcome to actually get the cell line you're wanting. Then quality. The cell line is often used to manufacture the therapeutic and often to support clinical trials. So you're immediately moving into GMP compliance. That first batch has to be GMP compliant, which typically tends to put you on the critical path. So developing this cell line is also important from a program perspective. And thirdly, productivity. It's not just enough to have a cell line that produces the right molecule, it's got to do it to high quality and at high titer to have any chance of commercial success. So these are difficult known challenges, and there's a real need for innovative solutions to accelerate this process and to accelerate cell line development. So today in this talk, I'd like to introduce Cyto-Mine, our platform that overcomes some of these challenges, and how this novel approach provides a real step change in cell line development and the success of that process. So let's start with picodroplets. What's a picodroplet? It's a small diameter, so we're talking about 50 microns. It's an aqueous droplet in oil, and we produce these using microfluidic chips. And you can see on the slide here various videos of our technology in action. The point is, this gives us easy to produce, highly uniform miniature bioreactors. We're talking thousands a minute rates of production. Then you can add cells, one per droplet, and you've got the perfect system to give you a large population of cells and to analyze them, but genuinely need to analyze each individual cell. So it's the best of both worlds, large populations and single cells. We're avoiding averaging effects. We're really finding the single cell you care about. We have a lot of proprietary chemistry around this because you have to have stable biocompatible droplets. For example, gas exchange has to occur to keep the cells happy. But once we have the droplets, we can perform all sorts of various unit operations. We can store them, split them, select them, dispense, and so forth. You can see the various videos here of us doing the generation process, the selection process, dispensing process, the addition process. This technology is validated on many different cell types: mammalian cells, so CHO cells, primary cells, Bs and T cells, yeast, bacteria, lots and lots of different types of biology that you can pop into these droplets and start to use this technology. So let's look specifically at the workflow that we've put into Cyto-Mine, so how we actually take these unit operations and put them together. So the process starts with a cell population, say 500,000 to 1 million cells in some nutrient-rich media, and those you pipette into the cartridge. First part of the process is the generation of the picodroplets. So we encapsulate those reagents into the oil with our surfactants that stabilizes it all, and you build that population of droplets and cells. We then allow those to incubate, typically 37 degrees C, and that's to allow the cell to start metabolizing, doing the processes and producing the molecule of interest. So you can see here in the cartoon, that cell is in a good environment. It starts to express, in this case, we're producing an antibody. So we hold them and incubate them for as long as necessary, usually a few hours, 2 to 4 hours to get that process running. We then move to measurement. So we are looking at each and every single droplet with a cell in it and measuring a signal. We typically use fluorescence using a forced to resident energy transfer approach, where we're looking to see a structure has been created and that's allowing the energy to transfer, so we can see if something of interest is in the cell, and we can actually measure that. And if it's one that's produced something, we can select it. Once we've done the selection process, we're then able to image those and dispense them. And so at the end, you have a well plate with individual cells in each well ready to move on downstream to your next set of processes. So where we started with, say, 1 million cells at the front times 0, within a few hours, we've gone down to, say, 1,000 cells, 384 well plates. So 1,000 to 1 enrichment on the basis of interrogating every single cell in that population. So this is done using our platform Cyto-Mine, and this really is the world's first fully integrated platform based on this microfluidic Picodrop technology. It's easy to use, it's robust, and as I said, it really lets you take large cell populations and screen them at the single cell level. Cyto-Mine is really a great example of where we're taking what was always known as a lab on a chip and actually making that available to everyone, not just being a massive lab around it to actually make it run. We had to solve a lot of technical challenges here. There's chemistry, there's hardware, there's software, there's manufacturing. But a typical run, you'll do it in, say, 3 to 7 hours, depending on your incubation time, and a typical cost of around $1,500 per run for cartridges, reagents, and so forth. So if we actually look at the Cyto cartridge, this is a big part of the technology. The machine is the obvious thing, but this is really starting to get into the heart of it. It's fully integrated, a fully integrated cartridge that carries out all those processes I was just describing, all mass manufactured, all to the quality and the standards you'd expect for the kind of work that's being done. So it's got all these parts of the process where you load your sample, where we encapsulate the incubation area that we were looking at, where we do the sorting, and where we do the imaging. And that particularly leads us to monoclonality. We'll talk about that a little bit later, and the dispensing process at the end. So all the materials are cell compatible, they're assembled in a clean environment, everything you need to maintain the quality of the cells to give high viability and subsequent outgrowth. Then looking even closer, the real heart of it, of course, is a bioassay. How do we actually look for some meaningful, some useful signal from the cell to make this selection process? There are numerous assay formats you can adopt for picodroplets. A lot of the work we do is around secreted targets because the droplet allows you to contain the secreted molecules. And as I said earlier, we do a lot of work around resonant energy transfer assays. So we've got examples here of one where we're looking at the IgG on an antibody, or one where we're looking at a specific antigen. They can all be integrated into the droplet and allow you to measure what your cell is doing. We can also do surface-based targets. So rather than a secreted molecule, something that's being expressed on a surface, whether doing something like a cell binding assay or some functional assay, that can all be integrated as well. One of the key benefits of the picodroplets is they are tiny, tiny volumes. Particularly when you're doing secreted assays, it is able to secrete and build concentration very fast. So we can get a very rapid increase of target concentration, so we can do very robust assessment quickly of what that cell is actually producing. Okay, so we've looked at the technology, we've looked at the platform, and you can see how this is working. Let's look a little bit more closely now of that in action, and particularly looking at cell line development, and particular case study with one of our customers who's using Cyto-Mine as part of their process for cell line development. So if we look at the quality and productivity challenges around cell line development, these really break down into 4 key needs: monoclonality, traceability, titer, and scalability. Do we have a single cell? Do we know where it came from? Do we get good quantity from it? And can we scale that out to what's really needed for mass manufacture? So let's focus at each of these needs in turn, and we can show what the platform does. So firstly, monoclonality. Obviously a real concern in cell line development work. The EU and US guidelines make it very clear the importance of single cell progenitors for any recombinant product. You know, this is expected. It's part of that managing of quality and confidence in product. The way we do this in Cyto-Mine is actually by assessing each droplet prior to dispense to confirm if a single cell is present. So what we do is we take 5 images of the cell in the droplet as it's passing through the channel. You can see that in the video there. The droplet is moving along. We image it multiple times. By taking multiple images, we're avoiding things like false positives where one cell might be shadowing another cell. We genuinely use the movement of the system to check multiple times, have we got one cell in that droplet? We use a machine learning algorithm to actually classify those images, and that's presented as a plate map, as you can see there. So we're doing this imaging, dispensing, and then you get a map to show you what the system has identified. So green wells are all as expected, single cell in the droplet and dispensed. Red wells, we know there's something not right. As you can see there, that one's got actually 2 cells in it. It does happen occasionally, but we recognize that, identify it. That's where it is. And occasionally the imaging, the classification is not quite sure. They've come out as yellow. So the user can then double check. All the images are stored. You can go back and say, let's see what we've really got there. Is that something to take for post-processing or not? So fundamentally in the system, we're checking monoclonality, and we're doing this through multiple images to be confident we really have got that single cell in the droplet dispensed into a well in the plate. Then traceability. So as well as confirming monoclonality status, we really did have one cell at that point in the process. We can also trace that droplet back through the selection process. So we can look at the fluorescence data that we use to select the droplet. So we have that traceability. This is how it was selected. It is only a single cell, and this is where it is in the plate. So this combination of the in-process monoclonality and selection traceability gives you that robust control of quality during these early stages of cell line development. You've got a solid foundation for later analysis and scale up within the GMP environment. Cyto-Mine itself is GMP ready. Our software supports 21 CFR Part 11 compliance. We have the qualification packages, IQ, OQ, PQ, everything you need to allow straightforward integration of this kind of technology into a GMP environment. So now let's look at the next question, productivity. Let's look at titer. So Cyto-Mine is genuinely looking at every cell, and it lets each one be assessed for productivity. So the example here is the FRET assay I was talking about, and here we're looking at secretion of antibodies. The antibody is secreted, the donor and the acceptor are brought together, and we get a signal. Now, we know the incubation time is the same for every droplet because we've held it for many hours, all under the same conditions. So we can actually get a donor acceptor response depending on the quantity of material secreted, and that you start to see on the scatter plot on the right hand side. So donor is on the x-axis, acceptor on the y-axis. Every cell has a different response. If the molecule is secreted, we're getting that transfer of energy to the acceptor. You start to get signal, and you can clearly see there's relative performance here. There's a large population that are not doing anything very much. Some populations responding, and at the top left-hand corner, a smaller part of the population that are really responding, a good high signal coming out of that. So you get that quantification. You really can measure and rank productivity of each and every cell in the population. And through this simple gating approach, you can then start to select those and say, no, I really want to take away from this process those very high production cells, the ones that are really giving us the signals that we want. So every clone is isolated, measured for productivity, and you select the high producers just through gating on a scatter plot, as you can see there. Let's look at the case study. We're looking to select high expressing clones. This was some work we did with our colleagues at AbZena, and a big thanks to them for all the work they've done and for letting us use this data today. So here we're doing a comparison of cell productivity. We're looking at a Cyto-Mine based protocol versus the current, the in-house process, which is limiting dilution with their in-house CHO cell platform. So 2 pools of cells we're evaluating. There's the 1030, which are known to be a lower expressing pool of IgG1, and the 4044, which is a higher expressing pool. So we're doing a comparison between these 2 processes, Cyto-Mine and the in-house process. So AbZena, they're a CDMO based also here in Cambridge, UK, and they're providing development services in biologics and bioconjugates. The big thing for them as a CDMO, every project they do is a customer project. They really need to identify their high producing cell lines quickly and efficiently. Very important, that efficiency of work for how they run their business. And they were interested to see what Cyto-Mine could do to really add value to their business and take them a step forward in productivity. So let's start by comparing seeding and outgrowth. So this table shows the 1030 and the 4044 cells, limiting dilution, LD, Cyto-Mine, CM. So the upper part of the table shows the seeding. So if you look at the monoclonal, i.e. genuinely single cell, you can see the much higher proportion of monoclonal in the Cyto-Mine data. There are many more cells at this point that were seeding out truly monoclonal. So you've got many more monoclonals there. There is an increase in polyclonals, but the absolute number, you still have so many more monoclonals to start with at this point in the process. And we know those ones are polyclonal, so you can capture them at this point, as we saw earlier with the imaging, and not take them any further. You're only taking the monoclonals forward. Then the lower part shows outgrowth data. So the 1030 is more prolific than the 4044. But in both cases, the Cyto-Mine is greatly increasing the absolute number of outgrown colonies. There are many more colonies available after the outgrowth process, about double the number. Note the percentages are lower per well using Cyto-Mine. This is not unexpected. This is relatively early data when Absena was starting to use this, and we often see that as you move into picodroplets, some of the percentages of outgrowth can be a bit lower than would typically be expected. That's recognized. There's some optimization. This is early data. Subsequent optimization has brought these figures much closer to what they were getting from their limiting dilution. So you can bring that proportion back up again quite easily, but look at the absolute numbers. Even at this early stage, there are many, many more colonies being derived and known monoclonal colonies at this point. So let's look at the titers. Data on the left is the lower expressing 1030 pool, the higher expressing 4044 on the right. So the 1030 pool has many more hits using both techniques. It's good growing post-selection, but ultimately it does have lower productivity. Proliferation, productivity are not correlated. There's no quantity shown because this is confidential data. So in both cases, the Cyto-Mine has identified a greater number of single cell clones, twice as many for the 1030, about 4 times as many for 4044, and the clones have higher productivity, significantly higher for the 4044, which was the lower expressing cell line. So the red horizontal line is just showing there the internal threshold to say what we call a high productivity clone. So the orange is the current platform, limiting dilution. Blue is the Cyto-Mine. You can see just how many more of those selected clones are above the threshold. So we've got more cell lines identified and improved productivity clearly in this data. We also should note, along with this improved performance, it also reduced the time required. It's about 40% reduction in time and about 70% reduction in screening cost, plus a much simpler process. So when you're in a busy, high-pressure CDMO type environment, these are real benefits. More cell lines, higher productivity, quicker, simpler, and cheaper. We really can start to see the benefit of the technology in this application. So finally, let's look at scale up. We found some really good cells. We've got confidence in their productivity and their high producers, but is that scalable? Can we actually take that forward into the much larger volume? So in this data, we're comparing titer of IgG between selected clones and a pool of cells. So the selection process, has it improved the titers? So we're looking at the various systems, the AMBER system, a 2-litre scale and 50-litre scale, the pool done at 50 litres. So we look first at viability, the lines. The clone cells all maintain the cell count beyond the 7 days, whereas the pool is starting to drop away. So through the selection process, we have got more viable cells coming out here. We then look at titer. The clone cells are clearly outperforming the pool in all circumstances, up to around a factor of 4 after 14 days. So what we've been able to demonstrate, we've selected high titer, high producing clones at 500 picolitre volume, and we scaled it to 50 litres. That's a volume increase of 11 orders of magnitude we're demonstrating here and maintaining that titer production. It's scalable. You really can work small and scale right out to true levels you'd need for manufacture. Another aspect, of course, is quality. we've got a lot of product. Is it the same product? So in this data, we're comparing the pool cell with the selected clones, and this is in the AMBER system at 15 and 250 mils, and their relative production of certain glycoforms. So the takeaway here, as you can see, across the different systems, the relative proportions of glycoforms is the same. GDF dominant, GA1F somewhat present. So going through the selection process has not changed the product quality in any way. It's the same product by this measure, but as you saw in the previous slide, it greatly increased titer and scale of the process. So by using Cyto-Mine, we have addressed the key challenges of cell line development. We have reduced the time and the effort to identify and select high-value cells. We have got the built-in monoclonality and traceability that underpins GMP. And we are finding truly commercially relevant, high-producing cell lines that you can scale and give you the quality that you need. So hopefully that gives you an idea of what the product can do, and some really nice data here from AbbVie. And as I say, thank you to them for sharing. That shows that in very real, concrete terms. Just to finish, I'd like to talk about some new work we're doing. So we've looked at picodroplets in terms of selection and automating cell line development. But what about creating libraries? Can we actually come further up the process? We're actually trying to create a library of cells to do the subsequent screening. So here at Sphere, we've experimented with both transduction and transfection. This is a transfection example, chemical transfection. We're implementing a workflow which uses Picodroplets, which is another product we have to do the encapsulation, and then Cyto-Mine for subsequent sort and dispensed. So here's the workflow. We're encapsulating the cells with CRISPR-RNP and with the transfection agent. We actually incubate offline for 48 hours to give that process time to work. And then we sort for GFP positive. And here we're talking 450 picoliters, about 95 microns in diameter for these droplets. A little bit more detail on the underlying assay. So this is a model system, HT116 file line, courtesy of the Horizon, or Revity as now is. So the cells are engineered to have a mutation that GFP is not expressed. And if the CRISPR process has worked as expected, that edit is made and the GFP is switched back on again, and we can start to see that signal. So we did about 350,000 cells encapsulated, the transfection miss with the Cas9 RNP along with a template, and ran this process as we just described. Before we did that, first check was just that the transfection reagents are actually compatible with the droplets. And so the data here is just showing a number of different transfection reagents and droplets under a microscope, just to show that their stability. And as you can see, in some of the cases, certainly after 24 hours, we're starting to see a reduction in the number of droplets. They're starting to burst, but mostly very good stability. So we're confident that the cells are actually able to sit for long periods of time with the transfection reagents and give us the stability we need to run the process. And then again, let's look at some data. So scatter plot, as we were looking at earlier. So here we're looking at the peak of green fluorescence and the average of green fluorescence. And when we've had that process has occurred, we've done the edit, you start to get a much increased peak fluorescence signal. So you can gate out on those and say what's actually done the edit and has the signal. So in this case, about 4.4% of the droplets were selected based on that expression of GFP. We've repaired the mutation. Middle data shows outgrowth and fluorescence after 14 days. So those cells have multiplied, and that edit has been retained. So we've maintained viability and maintained the edit. And the final data shows that repeatability. So we just did it across 6 plates. And the average outgrowth is 16% with a fairly tight standard deviation. So this is a pretty repeatable process, given that we're doing this for the first time. This is proof of concept data to show that this process is even possible. So the earlier part of our presentation, we showed the value of Cyto-Mine for doing the selection process, and specifically how that brings big benefits to cell line development. And then here we're moving further up the process and showing how this technology could be integrated to actually develop the library, and of course then move very easily into the downstream selection process. So thank you very much indeed. Thank you for your time. We've talked about Cyto-Mine and how our novel automation approach enables better cell line engineering, more clones, better and quicker and cheaper, and how we can extend that into library generation. Cyto-Mine really is unique in the way that we've taken chip in a lab to be an integrated product that lets you use these picodroplets. And it's a real high value approach for finding cells you care about. So thank you.